Welcome all. Today is about reinforcement learning. This is also one of the subjects that has progressed with great strides in the last few years. This was coupled to the progress that we've seen in neural networks. And you might have heard of some of the more famous applications recently. So in 2013, it first became possible to play video games with performance better than the average player. Late last year, we've seen AlphaGo Zero, the program that has been able to beat the previous best program at Go, which has beat the previous best chess player or Go player in the world. And this was remarkable because this became possible with no supervision whatsoever. And all of this is thanks to reinforcement learning. The actual algorithms are older, but thanks to, or the basic ideas are older, but thanks to infusing the power of deep networks, they now do so well in practice. So I have a few introductory examples. First, let me speak the grandmaster himself. So this is Sutton, who has also written one of the most famous textbooks on machine learning. And here he is giving a tutorial on reinforcement learning.
Let's go. Here you are. You're facing your world. I'm going to tell you a hint. You've got two actions. You can do action number 1 or action number 2. And I'm going to ask you what action you'd like to try. But
I like the example because unlike the robot ones and so on, where we humans easily see what problem the computer is supposed to solve or what the solution could look like, here, you know, the computer does know that he or it, it has two actions available, actions 1 and 2. It does not even know how many states there are. All it knows is that right now it's in state A, but it does not know if in state A it's better to do action 1 or action 2. So the computer can try one of the two.
You're now at time 0, you're in state A. Okay, what action would you like to try? 1. Good. 1. You get a reward of plus 10.
So this is great. So plus means, you know, positive reward, negative
life is good.
Be bad.
What action would you like to do next? Because you don't know if plus 10 is a lot or if it's a little bit. It's evaluative. It evaluates how well you did. It doesn't tell you what you should have done. 2. Minus 14. So what would you like to do now?
And that's a good question, because now you see now we are in state B. So it looks, even though the system may be stochastic, so from our experience it looks like action 1 here is better than action 2, but this is if we're in state A, it need no longer hold when we're in state B, and so on. Yeah? So the system knows, does not know the immediate reward associated with the decision, and it does also not know as a consequence of its action what will happen, if it will transition back to state A or if it will stay in state B and so on. Yeah? So everything's unknown to the system. So this is the hardest problem. There are easier problems. There is, whoa, this is really fat ink. There is, let me try and read this. The first problem, the easiest problem that we can try and solve is prediction, where we evaluate an expected reward given some policy. Look, I will just try and make this bigger, and hopefully this will make it more readable. Okay, so prediction is the first class of problem. We try and evaluate the expected reward given a policy. And we need to know for this the world model and the policy also. Then in the second stage, for planning or control, we are given a world model. So we know that if we're in action A and we choose action 1, with which probability will we end up in state B, for example. So we have the world model, and we're trying to find the optimum policy under this world model. And then in the third line, reinforcement learning is the hardest problem of them all. We want to maximize the expected reward over all of time without, however, knowing the true world model, without knowing the consequences of our actions initially. So a very difficult problem. And then let me show you some more successes. So this is from a paper, maybe this was 2015. Robots learning to stand up and walk. And so the robot knows something about its state. So this is the relative angles of its kinematic chain. It also knows if it got a reward or not. So for example, here the reward could be, it's up to you what you make the reward, but it could be proportional to the time that it doesn't fall over, or proportional to the distance it has covered or so. And it's often helpful to give the systems also micro rewards. So not just tell it that the further you manage to walk to the right, the more scores you get, but also if you try to help it develop a bipedal motion or locomotion, you can give a side reward, let's say the height of the head. Yeah? So if the thing stands up, this is an extra cue that you can give to the system that this will help. Finally, I will show you my preferred version of this. It's the same thing, just with sound. And so on. Some of these, excuse me, some of these are a little mean. You can watch the whole video for yourself. And then, as always, on YouTube, it goes from bad to worse. So this is the next one that YouTube suggests. Here you can see how you have 2-player games. And they learn to push each other off the platform. They actually learn to. It goes on and on. You also have more human-shaped ones, and then they actually develop. So each human here has its own network or its own policy, and then they resort to different policies. So it looks like one of these robots actually learns to trick the other, like moving out of the way in the last second, and then the other guy, rushes past and into the water. Okay, so these are the more and less useful things that you can do with reinforcement learning. Now we'll get very sober. And by the way, I forgot my pen in the other building, so I can only type with keyboard now, or point with hand. Let's formalize all of this. We want to optimize the decisions in a sequential decision process. And the simplest possible sequential decision process I have shown here as a so-called directed probabilistic graphical model. In this case here, I have shown you a finite Markov decision process. So one with just finite means finite length. Yeah? So we have here a sequence of 5 time steps. At each time we have a state. At each time we can take an action. The action will produce an immediate reward, positive or negative, but it will also impact how the state evolves over time. So the state at time 2 is a function of the state at the previous time, but also of the action we took, and then the same pattern goes on and on. Okay. This one I have from the book by Jensen and Nielsen, and the example they give is that of developing a fishing policy for a country like Norway. So the state could be the amount of fish that they have in their coastal waters. The action would be the legislation allowing fishermen to this year haul in so and so many tons of fish, and then the fishermen make money, and from this money they pay tax, and if they're happy they might even re-elect the politician who made the law. Okay, so now there are different kinds of politicians in the world. Like a short-sighted one may say, okay, I'm 60 now, I want to be elected one more time, and afterwards I will retire. So the interest of a short-sighted politician could be to maximize the reward, let's say, over these 5 years. And in such a case, if we want to maximize the total reward for these 5 years, we can, I think, already qualitatively guess two qualities that the resulting optimal policy will have. Namely, on the one hand, presumably, the optimum action that we take in the first year will be different from the optimal action in the last year. So actions can be different from, or the optimal actions can be different from year to year. And well, secondly, that the optimal policy for a finite time horizon will be different from the optimal policy for an infinite time horizon. Yeah? So for example, if all we care about is to extract as much money as possible from the sea over the course of 5 years, then in the last year, probably we would want to catch all the fish there remains. Okay, that will surely be helpful in the final year, but we wouldn't like to do the same thing in the first year, because if we already kill all the fish in the first year, we will have nothing to eat and nothing to gain in the following few years. So we will probably want to be conservative here, and then increasingly aggressive towards the end. And that would be an optimal policy from the standpoint of maximizing reward for this finite period of time. By the way, in this very simple example here, the state is immediately observable to the agent deciding which action to take. And this is why it's called the Markov decision process. This is not always the case. Sometimes we do not have access to the true state, but only to an observation which is somehow related to the state. So for example, the true number of fish could be the latent state, not directly observable, but we could make a test catch early in spring, and if the test catch is rich, we will assume that there are lots of fish. If it's poor, then we'll assume that there is little. This would be an example of a partially observable Markov decision process, or POMDP, and I'm mentioning it here because you will see it in the literature also. So today we will start simple. We will start with finite Markov decision processes, because these we can solve exactly. So we can find the optimal policy here if we know how the environment reacts to all of our actions. So if we have this extra knowledge, then we can solve this problem exactly. And then later today we will talk about a setup where the process may take longer, so where we have infinite Markov decision processes, or also where the property of the environment, the world model, is not known to us. So, and here on the right-hand side, I've written what is under our influence and what is property of the environment. So the property of the environment, how the environment or how the world reacts to a perturbation or how to a certain action, this is something that we may need to estimate if we don't know it beforehand, but we cannot change it directly. These are just the laws of physics or biology or whatever. The only thing that we can do is to decide which action to take once we're in a given state. And the whole thing is called Markov decision process. So here, the state only depends on state and action at the immediately preceding time step. So we don't need to know further history to reason about what would be a good action to take next. Okay, now I've already mentioned that the picture above is a directed probabilistic graphical model, also called Bayesian network. And so far in the lecture, we have been discussing undirected probabilistic graphical models. Directed probabilistic graphical models have a somewhat different semantics, but they also allow to find compact representations for high-dimensional probability distributions, or to compactly express conditional independence relations. In the case of directed probabilistic graphical model, we can factorize the joint probability. So here the probability of all states and all actions and all rewards, they're all treated as random variables here. We can factorize this into a number of factors where each random variable only depends on its parents. So for each random variable, we look at what are the incoming arrows, and then we need to condition a random variable only on its parents, but not on its grandparents, and so on. Yeah? So in the concrete example here, we have a product over time steps number 2 to 5. And we say that the joint probability can be written as a product of the probability of a reward at time t given action at time t and state at time t. Yeah, so for example here R5 here is conditionally dependent on S5, or is conditioned on S5 and A5. And then A5 in turn is conditioned on its parents. So this is this term here. We have a probability of AT given ST, and I've also written here the parameters. These are the parameters that will tell what our policy is doing. And then we need to condition S5 itself. So here we have a term conditioning ST on ST-1 and AT-1. Okay, and we do this for all steps from 2 to 5. And for the first step, we have a corner case here. So I've written here for the first step explicitly the terms that we need. So the expression here in this second line of the equation looks much more complicated than the joint probability in the first line, but the argument is just like when we discussed the undirected probabilistic graphical models, that let's say when these random variables are discrete, then these conditional probability tables taken together are much smaller than the huge table we would need to specify the full joint distribution. Okay, so this is why they're used in the first place. Okay, now this is nearly a chain, but not quite. So if we look from a distance, it looks like a chain structured model, but then we do have these small loops. So what we can do is we essentially still treat this as a chain, but a chain which has composite nodes. And then we will send messages along this chain, just as we did in belief propagation in undirected probabilistic graphical models. Okay. So let's say the total reward, capital R, depending on the parameters θ1 to θ5 that tell us what are optimum actions in steps 1 through step 5, is a sum over all time points, t prime, and then we sum over all possible rewards. So different actions result in different rewards. So these RT prime are the rewards that we get from different actions at the same time step. And now these rewards we multiply with the probability of realizing that given reward, given our world model and given our policy parameterized by theta 1 through theta 5. So we essentially, it's a weighted summation. We consider the possible rewards and we multiply them with the probability that each of these rewards will be incurred. Now these probabilities, to write them out, we can marginalize out all the random variables except the one of interest. So here on the right hand side, this is the joint distribution, and then we sum out all variables except one. And this is the expression for the total reward, and now we want to find the optimum parameters, theta 1 through theta 5. And again, I think I should make this a bit bigger so the ink is not so bold. I've rescaled the size of this text, but without remembering that the ink does not scale along. Fine. Okay. So this we have a set of maximizations and we have a set of summations, and if we have in these maximizations, we will now try and push as far in as possible. This is something that we did when we were discussing belief propagation at the time. So first, I have collected here all the terms that involve this fifth time step here. And now we push in this maximization and the summations as far as possible. So for example, the summation over reward 5 only affects this one term here. So I write, and this one here. So I write the terms depending on R5 to the very right, and then sum over these. And the result is a message which now, after we have, so if you look at the terms above, they depend on R5, S5, and A5. After integrating out R5, the sole survivors are A5 and S5. Yeah, we now have a function of A5 and S5, or I write it here as a message M depending on S5 and A5. Okay, now this message, together with this probability of A5 and S5 on the top left, is something that depends on A5, which I can integrate out. And then I obtain this message here depending only on the state 5 and on the parameters theta 5 of the optimal action at state 5. And then I take the maximization and so on. Yeah, so these are messages. And because if we look at this term here, by the way, because here the maximization has already taken place, this tells us how good the different substates of S5 are if we take all optimal decisions afterwards. And this is something called the values of the substates in S5. And this is central to one class of algorithms in reinforcement learning. Yeah, so in reinforcement learning, we have two broad class of algorithms. One class of algorithm tries to figure out what is the best action to take, so what is the optimum policy. And the other alternative route is to estimate what is the value of a given state. And then just the naive policy is used to always, pick the action which leads us to the next, to the best state in the next step. And then this is the most modern class of algorithms which do both. They try and estimate both optimum policies and both optimum values. And this technology behind AlphaGo 0 is a representative of this class, where in their case, even a single network tries to estimate the value and the policy, optimal policy at the same time. Okay, but for now here we have this sequence of messages that we're sending, and indeed this is just an example of message passing or dynamic programming. So some of these things I've said already. For a bounded Markov decision process, bounded is defined as having a finite number of time steps. Optimal policy at each time can differ. And the opposite, I don't know if it's intuitive for you, it can be proven that when you have an unbounded MDP, the optimal policy remains the same over time. So when you are in a given state, in an MDP of infinite length, where the world model does not change over time, it does not matter where on the time axis are. If you are in state number 3, then you should always take the same action, no matter where along this axis you are. Okay. So bottom line, we can find the optimum policy by dynamic programming, provided we know the world model, which is of course a big assumption to make. So in the fishery example here, it's easy to write down a model for how next year's population is a function of this year and this year's actions, but this will just be a model, it will not be the true thing. So the policy is going to be optimal only if we know really the true world model, which typically we don't. Okay, any questions so far?
How do we initialize the initial states? How do we assign some values to initial states?
So that's a good question. How do we initialize initial state? If you look at this factorization equation here, we have a P of S1 here at the very end of this. And here, either you know it or you have to make an assumption. This becomes an extra parameter, just the distribution over states at time 1. More questions? So for a POMDP, we would not have a direct arrow here between state at time t and action at time t, but a state at time t would generate or would lead to an observation at time t, and then we would condition our action on that observation rather than the state itself. All fine? Okay. Yeah, go ahead.
The only thing we know, like what we had here, is the probability is that we know only the previous state we were in. Do we make decisions according to only the knowledge of one state of the previous state? I mean, when you said that the random variables depend only on the parent,
yes,
not on the grandparent.
Yes.
Like, can you?
Okay. So So there is, let's say, if in a direct probabilistic graphical model, yeah? If we have random variables, if my model looks like this, then I will have correlation between A and C. But the statement is that A and C are conditionally independent given B. Yeah, so when I observe B, conditioning on the value of B, then A and C are independent. Yeah, so B transports all that C needs to know about A in a way. Was that the question?
And I mean, that makes it it makes it Markovian.
Yes.
That's the assumption that it is Markovian.
Mm-hmm.
And I mean, can you like why did we choose here to speak about the state 5? Like isn't the state 5 the last one? Like maximize the expected total reward for state 5. Like,
Okay, so
is what the state 5 is going to be rewarded when it goes to state 6 or?
so in this model here, it really ends after state 5. There's nothing coming afterwards. Yeah? And here I have started with the finding the optimum parameters for state 5, because the result of this is a message which depends on A4 and S4. So if I now want to find the optimum policy at stage 4, it's useful to know this message, yeah? Because it depends on some of the variables that will appear when looking at 4. More questions? Yeah?
In an unbounded model, can we still do something like this message passing? I assume that we have to discount future time steps, but I mean, we don't have a point where we can start the passing, right?
Yes. So there are several problems in the unbounded case. One is that, like you say, we have no place to start from. What we can do is, or it is possible to prove that the optimum policy then is time invariant. But this also means if I look at it in terms of a graph, let's see if I can draw with, yeah, then I have a node for my parameters, let's say, and this node with parameters is then coupled to all the actions. And similarly, I will have a world model which is constant over time. And just if you look at it in terms of a graph, this now means my graph has become much more loopy. But a set of equilibrium or a set of equations are known which must hold in equilibrium, the Bellman equations. And then methods, iterative methods are used to try and estimate this. And this is the realm of these value estimation methods, or this is how they look at the problem. Okay, more questions? Good. Okay, maybe let's do one more thing before the break. Namely, a very simple approach when we don't know the world model. So now we're trying to directly optimize the policy, but we're going to use a sampling kind of strategy. So gradient-free policy optimization. The goal is again to find the parameters that maximize the expected reward. And I've here written strategy in words. We simply try out a couple of policies, not take steps. Let's say sample multiple policies under some model and see how good they are. And then we change our policy generating model in a direction that feels better. Yeah? So in concrete terms, an extremely simple model is used for generating policy parameters, namely, as you see here in the first line of my handwriting, just a normal distribution. Not just normal distribution, which is a harsh enough approximation, but a diagonal normal approximation distribution. So this is the ISO contours are ellipses that are parallel, or the major axes of these ellipses are parallel to the coordinate axes. And well, in practice, I might have quite a few parameters in the policy. Yeah? So this is really a very harsh approximation to make. Now, under this normal distribution, we sample a couple of policies. Like, we're just sampling a few parameters here. And then we try out all of these policies. Yeah? So let's say each policy determines how a robot tries to move. And then we record for each of these trajectories, for example, how long the robot has managed to not fall over. Or if we wanted to learn to walk to the right, how far it has managed to walk to the right. And this we encode in terms of rewards. So let's say the larger the better. And then we select those policies that earned the highest reward. So maybe, let's say 20%. Let's say maybe the two policies which earned the highest reward were this one here and this one there. And well, then I would fit a new normal distribution just to these 2 points. This would be my new normal distribution. And now I sample new policies from this new normal distribution, and I try these out, and so on. Okay, so it's really an algorithm as simple as it gets. This is the baseline algorithm. Yeah? So if you want to try out a simple algorithm, then do this. So you select the top 10 performing parameters, you fit your normal distribution to these, and you iterate until tired. And then the mean of your final normal distribution when you did become tired, those are then your best guess at the optimum policy parameters. It is computationally hungry, but a good baseline as long as your parameters are not too high dimensional. Okay, and when your parameter spaces are too high dimensional, then we need to do better than this, which we'll discuss after the break. But before, do you have any questions?
Is our objective to maximize the expectation of rewards? Or why do we not maximize the reward instead we maximize the expectation of reward?
We maximize the expected reward because the system may or will typically have stochastic components. So let's say if you're in state 3 and if you take action 2, then the reward that we get from this can be stochastic. So you're not always going, even every time that you are in state 3 and then take action 2, you're not guaranteed to get the same reward number out every time. And then also there's this state to state transition which need also not be deterministic. And this is why we're talking about expected reward here. And well, if the trajectories are of infinite length, then the expected rewards would be of infinite length. So really this is used for episodic processes. Those are processes which either terminate after a finite number of steps, like you terminate whenever the robot falls down, or you can have a condition that checks if the system has ended up in a stable state. Like if it always oscillates between two states, and then you can detect that and say, okay, we stop the rollout at this point.
And in order to get the expectation of rewards, so we just select the rewards to run a few times, and then we sum them up and divide it by the number of samples, then we get the expectation.
Well, usually for each, this is like the difference between a random variable and a realization. So even though the system is stochastic, each realization is just a single path, or is just a single trajectory. And here we are taking a whole bundle of these trajectories, each one parameterized differently, and then we see which parameters did well. If we wanted to know for a given theta more precisely how good is its reward, then like you say, then we would use multiple simulations from the same starting state using the same theta. But especially in the early stages, there's no guarantee that your theta is going to be perfect, so there's no point in wasting too much time knowing exactly how good it is. So it's more typical to just run different simulations or rollouts with different thetas, just one simulation each for every theta.
And how about the initial state? Do we also use a different initial state with different parameters, or we use the same initial state with different parameters?
So if later in the real world, if you don't know the initial state in the real world example, so it depends. Like if you're trying to tell the system to learn boxing, then the boxer might always start in the same corner. No? But if you try it to teach to drive a car, then you're not always going to start from the same parking lot, and hence you would start with some distribution over initial states.
I have a question, because you drew the Gaussian as like a two-dimensional one. So for example, if we have like 5 parameters, would we then have like a 5-dimensional space from which we pick?
Exactly.
Okay. Oh, so you pick like all 5 features in one go and then test them? So
Yes.
Yeah, okay.
Mm-hmm.
And how do we choose the mu and the diagonal sigma in the Gaussian?
Initially, you mean? Well, initially, we just guess some parameter. Yeah, let's say in the worst case we make every theta identical to 1, and the diagonal matrix initially will just be let's say all ones, and that's it. Okay, and now once you've run your evaluations and you've selected the top 10%, then you just find the center of mass of your top 10%. This will give you your new mu, and you estimate the spread in the different directions. The variances will give you the sigmas. Good. Let's have a break here, and then we look at a more advanced solidity after the break.